Okay, we're going to take a little bit of time and go through the homework problems for the independent samples tests. So let's take a look at this. Homework problems. You can find all of this information if you go to, let's go to Unit 4. And overview, you can download the independent samples worksheet. Or you can go to independent samples and download the independent samples worksheet here. Another thing that you're going to want is go to printable resources, and you're probably going to want the hypothesis testing decision tree. So we're going to download that. And then the critical values diagram, so let's download that. And then we also might need the t-chart. That should be all that we need, so I'm going to have those down at the bottom. Actually, I'll open them up just so I can have them up and ready to go. So those are the three documents that you will most likely need. And so we'll open those and have those available. So let's go ahead and get started with the worksheet though. So this is this right here is a problem from the book. And let's take a look at it. The known standard deviation in a salary for all mid-level professionals in the financial industry is $11,000. So what I like to do is, as I go through things, I like to make notes of what it is that I'm looking at. So I'm going to just make a few notes. The known standard deviation in the salary of mid-level professionals is $11,000. So I'm going to highlight that, and I'm going to do insert. Or sorry, I'm going to pin that, and then I'm going to do review, new comment, and then pop SD. So I've got the population standard deviation, and then company A and company B are in the financial industry. So what we have here is we have population 1, and then right here we have population 2 are in the financial industry. Suppose samples are taken of the mid-level professional company from company A and from company B. The sample mean for every salary for mid-level professionals in company A is $80,000. Okay, so what we have right here is mean for population 1 is 80,000. Okay, and then let's come up here. The standard deviation, what is it? $11,000. Okay, $11,000. The sample salary for mid-level professional company B is $96,000. Okay, so let's highlight this. New comment. Mean for population 2 is $96,000. Company A and Company B management want to know if their mid-level professionals are paid differently on average. Okay, so what is it that we want to know? We want to know, are they different on average? New comment. What we want to know is whether or not these companies pay differently on average. Okay, so it's just a really good process to go through and just highlight and note what it is that you're looking at. Okay, so let's look over here. Let's take a minute and make sure we know what test we're running and why. So what you need to do is pull out the hypothesis testing decision tree. Okay, so at the very top, you've got two questions. Are you dealing with frequencies, or this right here is continuous data from samples or a population, and then this over here is dealing with frequencies. And so we know that we are dealing with continuous data because we've got company A and company B with what are the mean salaries for two different companies. So that's continuous data, and we're looking at their means. Okay, so the next question is, are you examining the difference between groups or between a sample and a population? And so we are looking, and right here you'll see on the decision tree it says, you know, because we went to the left-hand side, so let's highlight this and say, okay, this is where we went. The next, am I examining the difference between a sample and a population, or am I examining the differences between groups? And the answer is we're looking between company A and company B, so therefore we're looking between groups. In other words, the same exact person, do you have two scores for the same exact person or for the same exact, you know, observable linked record? If you do, then you compare those responses together. But if all that you have is the mean of group 1 compared to the mean of group 2, and there's no way to pair them up, then independent is the way to go. So you say yes or no, and the answer is no. They are not being, the same participant is not being sampled more than once. They're only being sampled once. And so we're comparing one group to another group. The next question is the number of groups. If we have more than two, then you would do something else. But since we only have two groups, what we're going to do is the independent samples test. And so down here you can see this is the fun little path that I took. And it brought me to the independent samples test. And it will bring me through this all the way down. Now, we have, we'll go back to this. We're going to follow the 6-step process, and the way that we're going to follow the 6-step process, which is also outlined right here. But we're going to follow this 6-step process on this fun little sheet right here. Okay, first of all, what is it that I want to know? I already wrote this out. What do we want to know? We want to know whether or not the companies pay different on average. Okay, so we're going to put that right there. Okay, next, what is the null and alternative hypothesis? Okay, in order to find how to write the null and alternative hypothesis, this is a little bit different than the single sample test. Okay, with the single sample test, we were comparing a sample to a mean, compared a sample to a population. Now we're comparing a population to a population. Mu1 is less than or equal to, greater than or equal to, or equal to mu2. In other words, sample 1, let's do this, Control C, Control V, and then Control C, Control V. So, and let's make this subscript, home, font, subscript, and press OK. So we've got mu1 is less than or equal to, what is it that we want to know? What we want to know is, are they different? Are they different? And so if we want to know are they different, then we know that it is a two-tailed test, and that the null hypothesis is going to be that there is no difference between the two. There's no direction at all. It just says, are they different? And then the alternative hypothesis is going to say that there is a difference. Okay, and you can write this a few different ways. You can write it A and B, because we're dealing with company A and B. So if you do mu sub A is equal to mu sub B for hypothesis, for the null hypothesis. And what does this mean? What this means is there is no difference between how much company A pays compared to company B. And then the next one for the alternative hypothesis, saying that there is a difference. There is a difference between how much company A pays compared to company B. Okay, so the next question is, what is the level of significance, or the alpha level, or the probability of committing type 1 error? So coming back up here, I don't know if it says what it is that it has. So sometimes you just have to choose. So what we're going to do is we're going to say, you know what, we're going to choose with only a 5% chance of saying there is a difference when there really is not a difference. So we'll save that, and I'll save that and upload it. But so that right there is, there's a 5% chance saying that there is a difference when there really is not a difference. And so the level of significance is going to be 0.05. Okay, what is a test statistic? Well, the test statistic, the way that we determine what the test statistic is whether or not we have the population standard deviation. If we have the population standard deviation, then it's going to be z. If we don't, then it's going to be t. So the known standard deviation, in other words, the population standard deviation, is 11,000. Because we have the population standard deviation, the test score, or the test statistic, is going to be z. Next, what is the decision rule? Okay, so the decision rule is, we're going to pull something out really quick. The decision rule, we've got the critical value diagram, and this is a two-tailed test. And you notice I have these decision rules literally written out, and so for a two-tailed test, it's almost always going to follow this exact setup. For one tail upper, it's going to follow this setup. For a one tail lower, it's going to follow this setup. So just follow it right along. So the decision rule is, for a two-tailed test, I'm just going to copy this, and I'm going to go back to here, and I'm going to say, okay. Decision rule is, reject the null hypothesis if, here we go, we're going to copy this. zcalc is less than negative 1.96, or if zcalc is greater than 1.96. And what we need to do is we need to make sure that we're using the right values. So basically what we're saying is reject the null hypothesis if the calculated value of your z statistic is less than the critical value, which brings us to our question of what is the critical value? Okay, what is the decision rule? What is the critical value? And I probably should have calculated it right here. What is the test statistic and critical value? So let's do z is the test statistic, and the critical value is, let's go to the critical value, with a 5% chance of type 1 error, it's going to be plus or minus 1.96. So let's just copy that. What is the critical value? Plus or minus 1.96. So we've got the critical value, and now we have the decision rule. So the decision rule is reject the null hypothesis if zcalc is less than negative 1.96, or if zcalc is greater than 1.96. Okay, and then fail to reject the null hypothesis. So fail to reject the null hypothesis if, we're just gonna copy and paste this, if zcalc is between, equal to or between negative 1.96 and 1.96. And so this is exactly how you would write it, and I'm going to show you really quick what this would look like. So we've got the decision rules. And so I'm going to put this right here. Okay, so this is I should have moved this out of the way. It says draw and label the critical values, test statistics, and p-values. Okay, so we're going to just put this right here. T-crit, so we're going to use z-crit. We're going to get rid of all the rest of them. Z-crit equals negative 1.96. And the reason why this is on both tails is because it is a two-tailed test. If it was a one-tailed test, it would only be on one tail. Okay, and then z-crit is 1.96. There we go. And then what we have here is the region of rejecting the null hypothesis. In other words, rejecting the region, if we have a z calculated value, If we have a z calculated value that is in the green area, anywhere in the green area, then we are going to reject the null hypothesis. If we have a z calculated that is anywhere in the middle, we are going to fail to reject the null hypothesis. And so what we're going to do is we are going to find the z calculated value. We're going to find the z calculated value and we're going to put it on this as well. So what is the z calculated value? Reject the null hypothesis. Okay, formulate your decision. We're going to compare the test critical to the test calculated, or you can compare the p-value to the alpha. Okay, if the probability of occurrence is less than the alpha, then it's significant, just like if the calculated value is more extreme than the critical value, then it's also significant. And you can read through all of this. This is just more information that really tells you this is how you need to make your decision. Okay, and just sub in, instead of test, you need to put in, you know, chi-squared or z or t. Okay, so what is the value of test calculated? And we already have the value of test critical. So the critical value, we're just going to copy this, bring it down here. Critical value is plus or minus 1.96. And now that we've got the critical value, we need to look at the calculated value. And since we're dealing with the z-calc, there is a very particular formula for how to determine z-calc. And if you look right here, this is the formula for determining z-calc. There's once again a few different ways to write this. We can do it like this. Here, this right here is the standard error. The standard error for independent samples tests. And if you want to take a look at how to calculate the standard error for independent samples test, we can come to your textbook right here, the online textbook, and we've got the standard error for independent samples, where we have the standard deviation of the first sample plus the standard deviation of the second sample, or standard deviation over the size of n1, or the sample size, plus the standard deviation over the sample size of n2, and divided by, and taking the square root of that. Okay. However, in this case, we don't even have to do this, and the reason why is because the question already gives it to us, gives us the standard deviation of the companies, and the standard deviation of the companies is going to be 11,000. So it says standard deviation, or you can say standard error of, you know, it basically is treating it company by company. So let's do mu sub A minus mu sub B. So mu sub A is 80,000, and then mu sub B is 96,000. So that's going to be 80,000 minus 96,000. So that's going to be 16,000. And 16,000 divided by 11,000. So let's pull out our nifty calculator. And we're going to do 16,000 divided by 11,000. It gives us a z value of 1.455. Okay, so z equals 1.455. Oops, that's supposed to say equals 1.455. Okay, sorry, I've got Lizzie with me now, and she is struggling to fall asleep here, so you can see Lizzie. Well, there we go. And you say, hi, Lizzie. Yeah. So she starts crying. Yeah. So we've got a z value of 1.455, and in order to determine the probability of that, we're going to come right here. we're going to get the Z chart and open this up, and we're going to say, okay, what is the probability? And we're going to come down this right here, and it says 1.4, and then count over, and it's going to be 1.455, so it's going to be somewhere in between these two right here. So we're going to 1.455, 1.455, 2, 3, 4, 5, 6, 0.0735, 0.0. And so we've got the p-value right there, and so the alpha of it's okay, alpha of 0.05. So if you compare the two of these, then you're going to be able to see that you've got the alpha. It's okay. It's okay. You've got the alpha of 0.05 compared to the p-value. It's whatever. Okay, so we've got a p-value of 0.0735. So I put the p-value right down here, and I put the alpha value right here. And if we look at this, we know since the p-value is greater than the alpha, since the p-value is greater than the alpha, it is not statistically significant. And so that's basically what we're using to find out whether or not it's statistically significant, is the p-value. And so this is basically saying the probability of this occurring, and let's see if I can do this. The probability of getting this result, assuming that the null hypothesis is true, is 0.0735. Okay. So that's the probability of getting the result, assuming that the null hypothesis is true. So in other words, the difference between the two of them is what I just said. 0.0735 is the probability of that occurring. And the probability of what? The probability of getting this result, the probability of having a difference of 16,000 between company A salary and company B salaries, assuming the null hypothesis is true. In other words, assuming that they are the same, is 0.0735. Okay. So what's our decision? Tell me what the decision is. The decision is we fail to reject. I'm going to once again do this. Reject the null hypothesis and are unable to demonstrate that there is a difference between company A and company B starting salaries. Okay. Because the z value of the z calculated value of 1.455 is not beyond the z critical values of Okay. Last but not least, it says interpret your results in a way that you would tell your boss without using stats terms. You can use terms like average, difference, and other terms that are easy to understand without a stats background. We kind of already did this. Okay, so the way that we would say this is we are not able to demonstrate that there is a difference in salaries between company A and company B with the present information that we have. Company A's salary on average is $16,000 less than company B's average salary. The probability of having a difference of 16,000 between company A's salaries and company B's salaries, assuming the null hypothesis is true. So let's get rid of null hypothesis. Assuming that they're the two companies are the same, is about 7%, 7.35%. Okay, so this is what we conclude. This is what this really demonstrates more than anything. So this is the first question. Hopefully this was beneficial to you, and then I will come back and I will do the subsequent questions as well. So let's save that.